Cool, cool. All right. We are working on dual core symmetric multiprocessing. Let's have more than one CPU at the same time, which is something that I have been putting off for a very long time because I had a whole mess of concurrency problems just on one core. So going to 2 was not high up on the list. But I recently made a big effort to fix a bunch of those concurrency problems, and so let's see. Let's try for dual core. I don't know. I got the Hey Egoist, I am doing well. Hope you are too. We got lots of resources up here on the second half of the screen. We've got the OSDev wiki for symmetric multiprocessing. We're going to sort of base where we're going off of this code, hopefully. I mean, this is a disaster of code, but we're going to use some nice helper methods and make this look a little less horrific. We got the APIC documentation, got the compiler explorer in case I need to check anything. Actually, I should pull up the Intel documentation, the Intel manual. We'll probably need that at some point. So where are we? Well, the first thing, so I already did a bit of work here, just some of the stuff that I thought was going to be really boring, like writing out all of these constants, and I was able to, I wrote enough code to be able to, or actually more accurately updated enough code, not APIC, but ACP, to be able to print out the tables that the CPU gives you when you want to find out how many cores you have. So this was all just sort of mindless. I have a structure, I need to print that structure. But the thing that it got me is if I run, I've added this -s flag. -s means I want 2 cores, so that adds SMP2 to my emulator command. And when I run with 2 cores, I'm now printing out all of these ACPI tables. ACPI is the Advanced Configuration and Power Interface, I think. But one of the things that it gives you is information about the system state. And so this is the contents of the tables. It's all kind of nonsense, but we do find this table, the APIC table, which is technically not called, it's called the MADT, but the identifier is APIC. And that tells us that we have, among this huge list of things, we have 2 of these entries of type LAPIC, or Local Advanced Programmable Interrupt Controller, 1 for processor 0 and 1 for processor 1. So that's as far as I am basically right now, is I can tell you that there exists a processor 2, processor ID 1, but I have not sent it any interrupts. I have not told it to start running, so it's just sitting there waiting. And I think we could pull some information from QEMU about it. Like I could say not CPUs. I mean, that doesn't tell us anything useful. Somewhere in here, there's probably a way to find out like what it's doing, and the answer is going to be nothing. That's not very useful, though. So let's see if we can't sort of hack our way to sending it an interrupt. So I've just first got to make sure that, I think I'm going to leave these in the header for now. Just got to make sure these functions are callable. So I'm taking some of the functions that I wrote earlier and turning them into a header just by deleting all the contents. That's not callable. So the only API that I've defined here so far is initialize a local APIC. This should be static. Send an init interprocessor interrupt, and then send a generic interprocessor interrupt, which this is all just taken straight from here in the OSDev wiki. So I do need to fix, that's not the right one. Wanted this to be static. And so now we can go to the main file and I can call those functions. So what do we need to call? This tells me that we need to send. I don't need to worry about, well, I do need to worry about this a little bit, but for now we're just going to hard code ID1 because we can see that in the output. I'm going to worry about making this generic later. I have nowhere to send them right now, so we'll have to see. I know the startup IPI, the startup interprocessor interrupt, is where you tell it where to jump. I don't have anything prepped for that, so we'll have to get there in a second. But I want to at least send this much right now, which is the init interprocessor interrupt, which is the thing that I was just poking at. And that should be, because I wrote all of this, well, there's an interesting question. I was writing it as though this, whoever has written this code for the wiki has done all of this masking, so they're only updating this one field and leaving everything else the same. And it looks like the reason they're doing that is that everything else is reserved. I don't think I'm gonna bother right now. That's probably something that should be like a to-do because it might break real hardware. But for now, I think I'm gonna hope that that doesn't really matter. So theoretically, unless I've messed up my naming, we'll extend init. Theoretically, that should be, well, we need to make sure we initialize the subsystem. In initializing the system, I should probably do this clear errors line. So let's go ahead and make sure that we do that. I also haven't fixed. Well, that's probably actually already working. I don't, this person has like not used the symbolic names, which is not particularly helpful. 280 is the error status register. And yes, I need to tell it that this exists. Which of course means we're then gonna turn around and get every compile error imaginable. Yep, pretty much. No atomics, that makes sense. Just need to import that header. Still no atomics? Huh? This I know how to fix. Why are there still, is that not atomic, right? Nope, that's not helpful. Atomic store, that's the problem. You want a pointer to an atomic? I can give you a pointer to an atomic. I don't know if this is technically, certainly the typical behavior for a memory mapped IO like this would be to use a volatile and just write through the volatile. I think my read of the standard is that the memory model of atomics is compatible with the volatile model, and I think this is probably sort of clearer and more explicit as to what I want the abstract machine and then the real machine to do. I don't know that that's right, but it's also, I mean, I'm sort of trying it out here, and this is 2 lines of code that I'll need to update just to say, you know, volatile, just like, I mean, I could just basically do exactly what this person is doing, right? Star volatile UN32C star, right? I could totally do that. I want to try using this. We'll see if it works. Basically, that's basically where I'm at. That needs to be send IPI implicit declaration. Means typo. Init. Very British. Probably not. Okay, that should actually crash. That's totally fine because I didn't actually give it the second core. I wouldn't have expected it to crash in init though. Fault writing data 280. 280 was that error register because of a protection violation. But it's a page fault. I mean, did I make these things read only? I did make these things read only. Okay. So that's not very convenient. This map obj function is basically intended to it's intended to make it easy for me to just like map I originally wrote it for those ACP tables that we saw, that they're sitting in physical memory and they have pointers to physical memory. So I was like, oh, I just want to be able to map that to real memory, to virtual addresses without having to like map the same page. And so I just sort of bottled it up in one function just to make that a little cleaner. But I made it read only, which is an interesting decision that I have made. I guess we'll just make another version of this that's writable for now, and we can sort of coalesce that later. I mean, I also want this to return a uinputter t, just because that's what I need now. So I guess we'll just call it that. And it's really as simple as just saying, well, I want to map it writable. And don't do pointer math. That precedence works. Modulo has a higher precedence than addition, so that's fine. Could add that to the header. WI. It doesn't like that. It's going to pointer to void. Ah, okay. Yeah, that makes sense. Because VMM hold is returning a pointer to void. Guess we have to do the pointer math anyway. I mean, that makes me really sad to be like casting it from a, right. In VMM hold, it's a, is a character pointer that gets cast to a void pointer. That void pointer comes out and I leave it as a void pointer. That could be made into, actually, that would make this a little bit cleaner, potentially. I could make this a character pointer. I then cast it to an integer pointer. Inside of pointer add, it's cast to an integer and then back to, or maybe a character pointer and then back to and then I'm casting it to an integer. There's a lot of casting going on here. And obviously, I mean, it all goes away at runtime, right? None of this is actually going to appear in the binary, but there's just a lot of casts. I don't know. I'm not a fan, but we will, we're not here to fix that. We can fix that later. So we're just going to sort of lament. Maybe I'll even add an item to my to-do list. I'll just say, vmem reserve and map obj is unclean. Okay, so we still have a protection violation, which is not what. Did I not call the... I bet I didn't call the function. I did all of that work, and I didn't actually do anything. I super didn't call the function. Well, at least we can get rid of this cast, because I made this version not need that. Okay, we don't crash anymore. Now, as we discussed a second ago, that I don't know where the interesting CPU info is in the info page, so I don't entirely know how we find out whether that did anything or not. Right? Because what we would like to know is like, oh, there's a CPU waiting for an SIPI. I don't even know what SIPI stands for, an SIPI. But I don't think we're going to get that from this. Because info CPUs just says the thread IDs. Info registers will certainly give us what's going on, but well, I mean, that's something. It tells us that it's halted. I'm not sure which. I think eflags 2 might just always be set. I'm not sure which bit that is. I would expect this one to have the CPU 0 to have interrupts. No, I would expect CPU 0 to have interrupts enabled, so we can't see which bit is interrupt disable. CPU 1 is in 32-bit mode, interestingly enough. I'm not sure I expected that. That, or maybe it just prints out 32-bit selectors. Or sorry, 32-bit registers no matter what. That's a little confusing. I'm also a little confused that the segments are populated. But these are not segments that I populated. This must be the bootloader, or even the BIOS must have put in segment selectors in a GDT. But I doubt any of these still exist. Yeah, GDT is at F6280, which is super not where my GDT is. My GDT for the main CPU is at 14B78. So this probably doesn't even exist anymore, which is what we have to, I mean, that's the first thing that we have to do when we turn on this CPU, is we have to initialize it and give it, or I mean, this code here in the example has a GDT. I just really don't want to deal with that. I mean, I have to, but it's not going to be fun. But why don't we send the SIPI, the startup IPI, I guess is what I didn't know, and see, like, I would expect it to probably crash the machine, but we can, that's useful data, right? Let's do it, right? So what's a startup IPI? A startup IPI is we had this in the APIC page. A startup IPI is bits 8 to 10, which is the type, is a 6. So 6. Vector is something I don't understand right now. The starting page. We'll need to figure out what is going on here. This person sends starting page 8 or 08, which I'm guessing means, considering there's a consistency here, I'm guessing that means that the top 2 bits of the segment selector, the top octet of the segment selector is the thing that you're sending when you say startup page. But I'm gonna want to confirm that. So let's see how easily we can find this. Oh, we might need to enable the APIC as well. APIC software enable flag, APIC EN. Ah, here we go. Bit 11 of, oh, it's a model specific register. Base MSR. So this time we actually super do have to make sure we preserve this value, because if we change the APIC base, it's going to change this value, and I really don't want to deal with that. So, and ditto, we might have some challenges if we write to this BSB. This may be unwritable. But I don't want to risk that. I would like to just leave it exactly how it is. So we're just going to read the MSR. I don't think this define exists, but we will make it exist because I don't know where this is. Question of precedence. Yep, that's exactly what I thought it was. And then we have to know what this is. And probably, honestly, the easiest way to find it is just going to be to search it, because, well, this isn't very helpful. This is just the same page that we saw before. Ah, the Rust. It's 27. And we're just going to put that in x86 CPU. I guess I don't have any of these defined in here. Well, we're going to start because this is where they should be. But that's all we need to care about for now. That's not actually called base MSR. There was a space there. Ah, it is. It's just defined in apic.h. Which I don't think I agree with. Ah, I see. Well, guess I did a bunch of this before. How much of this did I do before? Not very much. Yeah. No, they don't have different addresses per CPU. See, I didn't know what I was doing. So this is really, it's the right call to redo it. Yeah, I mean, enable, it's all, we can basically just delete this entirely. Which I should, right, there shouldn't just be an APIC file. There should be one file for the local APIC and one file for the IO APIC. Because the IO APIC is completely different. Very, very old code. Very, very old code. Okay. We're gonna... Very, very terrible. Okay. We're gonna go ahead and just delete this. Ditto this. We're gonna go ahead and delete this too. I think we're gonna go ahead and delete this too. Let's see if that gets upset with us. Well, it gets upset with us because I don't know what I'm doing here. We want to send IPI 6. That may not be memory. And destination processor 1. And okay, well, that boots. I'm not sure I understand why. Probably because it's, partially because we didn't do enough. You're supposed to, for some reason, I'm not sure what the exact spec is here. This says you're supposed to send startup IPI twice, with a delay. There is a discussion in this page talking about there being a real specification for this, but that the timing is too tight to be generally... The MP specification contains a standard method to start an AP. It is not recommended to be used because it contains very precise timings, which, if done correctly, can lead to several problems. Brendan, who's a major original contributor to the OSDev wiki, offers an alternative method, which would be done for each AP individually. Send IPI, wait 10 milliseconds, send SIPI, poll for a flag, AP's trampoline code with a timeout of 1 second. If it was reached, send another SIPI. If the AP managed to set the flag, the BSP should set another flag to allow the AP to continue. So we're gonna do two things. First of all, we're gonna do this. I'm gonna just add a little delay there. And we're also going to go into monitor mode so that I can say info registers all info and see what this is doing. Okay, yeah, nothing has changed, right? This is on the same line. So either our APIC is not enabled, or we're not sending the right commands, or we're not waiting long enough, or any number of other possible problems. Basically, it ain't working yet. But we have ways to debug that, hopefully. I don't need that anymore. The fact that it compiles makes me think we might want to commit this, though. We've done quite a few things here, including deleting the old apic.h. Fixing that. Yeah, I think we're going to go ahead and commit this. And I did disable cool. Cool. I think I do. I'm gonna spend a bit of time looking at the real documentation instead of just going off of the whatever somebody thought was relevant to put into the OSDev article. So just gonna kind of scan this to see. Well, see, there's the first thing that I needed to scan. Spurious inner vector is initialized to 0 FF. By setting bit 8 to 0, the software disables the local APIC. Well, I, operating on the advice of, yeah, okay. So I didn't read this. Spurious inner vector, offset is FO. The low byte contains the number of the spurious interrupt. You probably want to set this to FF. To enable the APIC, set bit 8 of this register. Bit 12 is set UI will not be broadcast. All other bits are going to be reserved. Okay, so that's extremely critical, and I did not see. But that's why we look at the real documentation. I want to set that to 1 FF in order to, right, this is the spurious vector register. FF is the vector that I want, but we have to set bit 8. We are also sort of, like I say, I expect the thing that I'm hoping to get here is crashes. Like we are well off the path as far as I've got 2 interrupt controllers working at the same time. Like all of this is bad. I'm trying very desperately to get to a crashy, right? I'm trying to spin up a second CPU in the middle of nowhere. Bad stuff. But it's not crashing. So that tells me, well, for starters, there is no second CPU. So no change in behavior. Yeah. So, and we also disabled this because I didn't want to commit with that going. So that's certainly not helping either. We're still not crashing, so. Never wanted to crash before. Yeah, no change. APIC will only respond to init, NMI, SMI, SIPI. Well, that's fine because those are things we're sending. APIC can still issue IPIs. Don't do that. So after it gets an init reset by either asserting the processor's init pin or sending an init IPI with the IPI delivery mode set to init, Processor responds by beginning the initialization process of the core in the local APIC. The state of the local APIC following an APIC is the same as if it is after a power-up or hardware reset, except the APIC ID and arbitration ID register is not affected. This state is also referred to as wait for SIPI MP initialization protocol requirements and restrictions. That seems very helpful. That's probably the thing that the OSDev wiki cautioned us against reading, though. But we're going to read it anyway. So let's just remember that this is 10.473 so that I can come back to it. PDFs are such a pain because you don't get an undo stack or you know, it does work. Well, cool. MP initialization. MP protocol is executed only after a power-up or reset. If the MP protocol is completed and the BSP is chosen, subsequent inits do not cause the MP protocol to be repeated. Instead, logical processors examine their BSP flag to determine if they should execute BIOS bootstrap code or enter wait for SIPI if it is an AP. That's what's happening. So the MP initialization protocol is like for BIOS writers, I think is what I'm understanding here. BSP sets the processor counter to 1 and broadcasts SIPI to all the other APs. That contains a vector to the BIOS initialization code at... Yeah, okay, so we did learn that is the thing that I thought was happening, that the initialization code is at 000 vector 000, where VV is the vector number contained in the SIPI. So it would be really nice if we could get something there. That would be very, very helpful. It would be very helpful to have some code there to execute. So let's see if we can do that. Do I have anything that goes below? Do I have anything below the canonical? I don't know that I'm putting anything in low memory right now, which might make this a little awkward. So this is the list of, this is the list of all of the symbols that are output in my kernel right now. So the vast majority of these are public functions and global objects. T is a function type symbol, I think. D, I believe, is a data type symbol. And then these are the values, right? So the value of the variable is kind of a hard way to describe it because that's a higher level concept, but there's a marker basically called TSS64 that represents data that happens to live at this address. And in assembly, we indicate that like this. In the data section, here's the marker TSS64, and then there's some data after it. I don't want to call TSS64 a variable because all it is just indicating where this is. And logically, all of these things, it's like a struct basically, and all of these things are sort of contained within it, but there's just different markers inside of that. it's exactly the same as the way these markers work for functions, right? You would jump to here. You wouldn't say the whole function is a variable. You would say you're jumping to this label in order to execute this code. But this is the list of them. And in order to have our startup code has to be underneath, has to be lower than this 100,000 hex. It has to be physically, in physical memory, it has to be lower than this hex 100,000. It has to be at, the example that the wiki person used was 8. That's 80. Yeah. Hex 8,000. Which, honestly, I should probably just duplicate. And that has to be in physical memory too, because this is going to be running in 16-bit mode, presumably, we think. Right now it's in 32-bit mode after running the startup code, but I believe when we actually send an init correctly, my understanding is it's basically going to reset itself back to 16-bit mode. We'll see how true that is. But we want 16-bit code at hex 8,000, which I don't have a way to do without I think we're gonna have to basically make a little bit of a special case. Again with the we can clean this up later. So this is the physical memory management routine area, and I think you never do anything with this until after you call pm init. So really all we have to do is just like claim the code, claim a page. We're going to claim hex 8000 because I'm copying. So that it doesn't get handed out, right? That's the really key thing. We don't want somebody else to be using this. And I am currently quite, not aggressive, but I just start giving out pages at the bottom available page. So if we go into the monitor mode and I can put info TLB, and info TLB is the command that gives us every virtual to physical mapping. So we can see, this virtual address is mapped to this physical address. And if we scroll way up, which actually we might not even output enough to see it all. Oh, right. So part of the reason there's so many of these is that for a large portion of the 80XXX, a large portion of 80XXX is mapped to the same thing. 8045E is mapped to 45E. That'll be the case all the way down to, I think, hex 100,000. It's that same border at the bottom of what I was using. And this is because this is the these are the files in the init file system. So this is probably the file init, maybe, I don't know, it's a file. And the way that I can tell you that is, well, the code, this is like kernel writable variables. I think this might be the kernel BSS. These are writable pages. And then the init file system, I say, no, that's not writable. And the A bit means that the page has been read by something in software. This is something that the CPU is doing for you. It sets this accessed bit, and you can use that for I can track how many times pages are accessed to do caching or to know what I should evict or stuff like that. That's why it exists, but there's a certain pattern here. You can see a bit, nothing, 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 a bit, nothing, 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 a bit, nothing, 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 a bit, and it's pretty consistent, right? Well, what could that be? That's the file system populating. That's me reading the file name of, let's say, the file sh, and then that says, okay, the next file is in this far, and the next file is in this far. So these A's tell me this is the file system, right, being read originally to populate. All of this memory has not been touched at all. I'm not entirely sure what it is, but it hasn't been touched at all. All of this memory has been touched and changed. So accessed is the A bit means something has read it. The D bit means it's dirty, means it's been written to. And that's, again, software could see the D bit and track this. It would be used for, say you had a memory mapped file and you wanted to know what had been changed. You can just look for all the D bits in your memory mapping. This is all going to be kernel code. Most of it's been accessed. And then here is the user mode pages. The thing I was looking for, I wanted to know what the minimum page that was handed out is. And I clearly don't have... Not entirely sure why that mapping exists. I wanted to see if we have mapped any pages below OX 100,000, basically. And all of that's actually going to be at the top, so this is not very helpful. Answer is yeah. So here, this is what I was talking about. That, say, this C000, this is the first, when I give out basically free addresses with VMM Reserve or VMM Hold, that's just a way to like take some address space that, I mean, address space is basically free. There's no reclaiming, there's nothing like that. And you can see that's mapped to C000, or this one is mapped to D000, A000. These are very, very low, 8.4. And if we weren't in monitor mode, we could get it to tell us interesting. Okay. What's actually in use according to the physical memory manager, of which the answer is we don't use the bottom page because we want null pointer accesses to fault. If we use the bottom page, access to 0 would be totally legal. So we just we don't. Well, there's no reason that I shouldn't use the bottom page of physical memory. That's interesting. I wonder why I did that. It might be related to... No, it's just type 1. It's just regular memory. So we should fix that. Yeah. Okay, cool. 1000 to 9F000 are in use. And that's what I want to make sure doesn't get... I want to make sure that that we don't in use the page that is used for my AP initialization code. And I think we might... I do not like this code. I do not want to use this code. I'm not going to use this code forever. And I'm certainly not going to distribute this code. But I think we're going to use it for now. well, actually, this might be more trouble than it's worth. Just because I need something that tells me if it's working or not. So we're certainly not going to commit and distribute this, but I think we're just going to copy this for the moment. Because I don't want to set up a GTT right this instant or anything like that. Yeah. Though, so the thing that might be more trouble than it's worth is this is all AT&T syntax, and this file is not AT&T syntax. I wonder if I can actually set, if I can say, like, I wonder if I can just disable that. Can I just say this is... Does that work? Okay, that's a little concerning. That the comments aren't the same. I don't know what assembler they used. But we can just fix the comments. And that appears to have worked, because now it's complaining about these symbols not existing. And that we can totally fix. I'm assuming BSP done is supposed to be external. I don't think I can do that there. I think this has to be actually defined outside. BSP done, it wants AP running, and it wants go ahead and just print that out. And then loop forever. Cool. BSP done is 0. AP running is 0. What is AP running? AP running is we're just going to spin lock on that. We will make these volatile just for shiggles. It's probably necessary. Still not going to, it is going to be okay with that. It's not going to be okay with that. Oh, it's super not okay with that. Okay. Yeah. Yeah, that's not great that this is going to be running in 32-bit mode. It's 32-bit code, but it needs to touch variables that live in like in 64-bit land. That's not actually going to work. So we're gonna have to rethink that a little bit. This is obviously not intended to be used if the operating system is already in 64-bit mode. I mean, no, I'm not going to try to do this before we get to 64-bit mode. I'm really not interested in putting more stuff in 32-bit land. So we'll just have to come up with something else. For starters, we didn't actually do the important part of putting this at 4096. And in fact, this says jump to, oh no, that's jump to it's AP startup. Well, the printf code is going to be a problem too, because this is 64-bit code. As is, right, there is no 32-bit printf, so saying just like print out that you started, that's going to involve a lot more. I mean, so how bad would it be to like send it through the same pipe? No, we can't send it through the same pipeline, can we? So if I jumped it to start, what would be the problem with that? Well, it would set up paging correctly. It would set up. Does start actually change anything in the page tables or anything like that? Doesn't look like it so far. It would jump to 64-bit mode. That would be fine. It would, I mean, I think, so problem number one, it's going to use the wrong stack. It's going to try to use the HH stack. Problem number two is it's going to touch the TSS. Yeah, it's going to break the TSS too. So yeah, we can't just send it through the same pipeline. But I mean, we need to do all the same things. That's the thing that's really annoying here. Is we need to have a global descriptor table. We need to have a local descriptor table. We need a separate task state segment. I do believe, certainly imagine. I certainly can't think of any scenario that would cause us to not need two, one for each chord, because the global descriptors, right, that's, I guess the global descriptor table itself I could see being the same, because right, this stuff is not going to change. The segment bases, the segment limits, what is code and what is data, none of that is going to change. The problem is the TSS, the task state segment. So that's in the GDT raw, and the TSS contains, where's my TSS? This is the TSS. The TSS contains like stack pointers, and that's not good because I can't have two CPUs using the same stack pointers, which I think means I need a separate copy of all of this. But none of this information is very clear. Ah, interesting. That this is the thing. So, right, this is the sequence when you know the number of processors. This is telling you to use broadcast init, broadcast SIPI, which is the thing that the wiki and Brendan tell us is not allowed. But that's why there's a reason that I don't want to do any of this, and it's that it's can we do anything? Yes, we can do something. The thing that we can do is we can do like an inc. Right, sure, this is code 16, but I should still be able to 16-bit increment, let's say AP running, and then jump, halt, jump. Not ankle, but like that's fine. Word putter. And we can't necessarily do it there, but that's okay. We are going to just we could try that. Right, it's not DW, it's .word in GNU assembler. Let's make this global. There's still a question of how we're gonna, it's not .word, there's a certain question here of how we're going to get that to write to the right variable, because if I go ahead and like copy this somewhere else, it's not going to be the right variable, unless that ends up being IP relative, and I don't think there are any instruction pointer relative writes in 16-bit mode. That's a very modern feature to have it in 16-bit mode. Yeah, I mean, the fact that nobody is talking about that means that it's not possible. I guess let's see what that assembles to. Oh, that's still unhappy. Is that happy? No, that's still not happy. I guess we're gonna just have to go with seeing the monitor mode tell us that it's running. And that'll be okay for now. So let's go ahead and kill all of the little supporting code that we wrote up here. Let's make sure that we kill BSP done, AP running equals 0, any of that, because we don't actually care. The thing that we care about is seeing it in here, which we do not because there is still something wrong. So what are we doing wrong? That's really the next question. I would really like to not unmask. We do still have to call pick init. Right, moving to the advanced interrupt controller, we do still have to init the regular interrupt controller. Just to remap its IRQs and make sure that it's not going to send spurious vectors, because it can still do that. So we still need to call pick init, but I'd really like to get this using the local APIC for things like the timer and the serials, though we might need an IO APIC for that. So that might not actually be very easy to just sort of move out of this world right now. Let's see. Obviously, this is not going to work at all in terms of doing anything. But it doesn't make a difference either in terms of the CPU starting. So let's see what are we doing differently than this says. So obviously we don't have trampoline code. We should do the mem copy at least. Because we did reserve this page and we do need it. Because we are going to tell it, yeah, we are telling the processors to go there. That's what this OX08 is doing. It's telling it to go to OX8000. So we do need to have code there. Which also means we need to map it. Should be all I need. There's no AP trampoline. It's just a void function passing void pointer to, yeah, well, there's nothing I can do about that. See, I know that's illegal, but I'm gonna do it anyway. That should have resolved in linking. I don't know why that's telling me that that's a... Yeah, it's telling me that that mem copy is reading 0. Did I name it that? Did I make it global? AP trampoline. So this is the disassembled code, and the disassembled code definitely says in binary in assembly code, it definitely says destination is OX 8000, size is OX 1000, EDX is the third register, and the first one is, or the second one, RSI source, is 0, which is not particularly helpful because 0 is not in fact what I want to read from. I would really love to read from wherever this function AP trampoline ended up. Hello? Okay, that was weird. My terminal has decided that it doesn't want to accept any input. Which is not really helpful. It's the keyboard is dead. One moment. I really can't explain that. For some reason, this keyboard just stops sending key presses now and again. It's really thrilling. So where are we? We're looking at right, we've written this function in assembly called AP trampoline, but for some reason when we try to read from it, we end up with 0, which, I mean, yes, technically this is undefined behavior because I'm converting a function pointer to a void pointer. So if this is the C compiler saying, well, you really didn't mean to do that, here's a 0, I'm gonna be quite upset. I mean, we're basically just copying what this person said. I guess we should potentially try taking the, well, so the first thing I wanted to try was just putting that in the text section instead of the low text section. It shouldn't make a difference, but it could make a difference. And it did make a difference. Yeah, okay. Yeah, I mean, that certainly should have still been in memory. It certainly should have still been. It probably wouldn't have been accessible, but it should have at least had a value for this. But for whatever reason, now we actually have, okay, thank you. We actually have an address there. So this should at least not crash immediately, and it does not. Let's add a second core and see if we get anywhere. No, still no change. Second core is still sitting at FDOAE in halt mode, doing nothing. So now back to comparing. Right, we've found one problem. Back to comparing what we're doing. In here. So we initialize the trampoline code, right? That matches this. For each core, well, we only have one core. We don't care about initializing the current core because we're only touching core 1. We clear APIC errors. I already did that in local APIC init. Select an application processor and send init IPI. That's happening inside of LAPIC send init. Wait for delivery I'm also doing. Let's make sure that we're waiting on the right register. Maybe that could be a problem. The register called, we want to be waiting on the register, local APIC plus 300. We are waiting on Await delivery. ICR2 is 300, so that's right. We are waiting for MMIO read of ICR2 and 1/12 to be 0, which is exactly what this is doing. We then want to send the same exact thing again. The only difference is it's 8, 5, which I think those shifts are correct for 8, 5. Instead of C5. Maybe they're not right. We could make this a little simpler. Let's just actually print out what we're sending here, because we have our sort of expected values from this example, C500 and 8500. I expect that what I'm doing is the same as that, but if it's not, I mean, who knows what it could be. So let's go ahead and print these out. The first command is -O10 X and command 2. You don't like printf not existing. We can fix that. Command 1. Okay, so I am sending a different series of commands. I'm sending 5, 5, and 9, 5, where this person sends C5 and 8, 5. What would C be? C, just to make me visualize it, I'm sending 1015. He's sending 11005. Well, that 5 is this init, right? And so that's 8, 9, 10, and then the 11 is clear. The next nibble, which is this nibble, is 12, 13, 14, 15. And he's sending okay, so I'm setting this bit. He does not set this bit. I guess the hardware probably sets it for you. I can get rid of that very easily. But this is the one that's not clear. It means that, so an 8 set for deassert, clear for deassert, otherwise set. So if it's an init level assert, it should be bit 14 and no bit 15. If it's an init deassert, 15 and no 14. Which I think means that what I'm doing matches. No, because that's 4585. Yeah, but the C, in order to have the C 5. Huh? Wait a minute. He's sending C5 for the assert and 8-5 for the deassert. How did I get 4, 5? This isn't even the right table. How did I get 4, 5? Four, set, unless it's an init, deassert. So I interpret that to mean, all right, no, we're going to the horse's mouth because this is local apex state, version register, handling local interrupts, issuing interprocessor interrupts. So, okay. So these bits are just completely different from what the OSDev wiki says. They're just wrong. Deassert is certainly not this. Or 115 is certainly not deassert. The question is just whether we actually want trigger mode set to level, and I think the answer is probably yes, that we probably want to set this to level triggered. Otherwise, why would we be doing a deassert? And that, I think, might be closer to matching C585. Exactly. Right. So it's this table is wrong. This should be set for all init interrupts and nothing else. It has nothing to do with whether it's an assert or a deassert, I think. So that at least that gets us consistency with this. So what else should we be doing? This says 10 millisecond delay after that. I mean, we could we can certainly, it says to do no delay is specifically noted between the init assertion and deassertion, and then 10 milliseconds after that. I've got just a little busy loop here, but we can certainly make it longer. And then this one, this says 200 microseconds, which is about 100 times difference. All right, well that's a little more. 10 million is a little more than 10 milliseconds. That's more like 2 seconds. That's also a little bit more than 10 milliseconds. So if that's, we'll call that 100 milliseconds. We'll say that 100,000 is about 10 milliseconds, and we'll say 10,000 is pretty close to 200 microseconds. Just sort of off the cuff, random thought. So, yes. So, we are currently, well, so in this case there is no second processor to start, but we are currently, I have fixed, it shouldn't necessarily crash the system anymore because I have given it somewhere to go. So now we actually have to go to info registers, and we see that nothing has changed. So now this says to pause 200 microseconds there. We might actually try that, do a little 10,000 busy loop here before we await delivery. And it doesn't necessarily say we need anything there, but I think I'm going to leave it as well. I should really abstract the busy loops if I'm going to get this cozy with them. m. No change. We are confident that these are correct, so we are now going to stop doing that. Actually, here's an interesting thing that we can check. Let's do SM, and then let's just like, you know, see if the pick is working or not. Is it even on? Local APIC state for CPU 0, APIC enabled, spurious vector 255. And then CPU 1, there's nothing set up here. This is all just nothing. Oh, that's going to be really... I think I named these backwards because it turns out you have to write to ICR2 first and then you write to ICR. So I named them the other way, but if this is going to actually have it in its debug output, I may need to put that back. So have I done all of these things? Well, we know that we have an APIC. I set the APIC enable bit. And we set it. Map it to virtual memory. I did that. We know where it is. And set bit 8 of the register of this. So, I mean, we can do that after the fact, right? We can write to it first. Enable it first. I guess that does make some sense that we would enable it first in the model specific register and then write to it after enabling it. That makes some sense to me. No difference in behavior yet. But I don't know that we're going to solve this today. Well, at least not right now. I think I need to take a little break away from this, look at something else, maybe read some of this documentation in a little more detail, because I don't want to sit here and bore everybody on stream just like reading all of this. So I think what I'm going to do is I'm going to cut the stream here. I'm going to make some lunch. I am going to read this documentation and take some notes so that I have some stuff like ready to try, and we can do some more interesting stuff the next time I'm on stream. That might be later tonight, or it might be tomorrow evening. I think probably one of those. But either way, I will see everybody later. Thank you, everybody, for coming along. I hope you found that interesting, and I will see you later.